Alright everybody, so today we are talking about acid-base calculations. So we're going to be able to do some basic acid-base calculations where we find pH, POH, H+, and OH-. We will be able to do it easier with some strong acids and strong bases, but then when we get to those weak acids and weak bases, we're going to have to do a little bit different type of problem solving in order to solve those types of problems. So let's go ahead and let's get into it. The first thing you have to know is you have to know about water. Okay, water, it is neutral. Okay, it also has its own Ka or Kb, but it's not called Ka or Kb, it is called Kw. So it has its own equilibrium constant, and the equilibrium constant of Kw is 1 times 10th to the negative 14th. Okay, water does dissociate a little bit. It will react a little bit. That's why your fingers get kind of pruny a little bit when you get in water. It's that water reacting with your skin. So water will dissolve you if you sit in it long enough. Okay, that's pretty much the lesson you should get from this today. But some good things about Kw is Kw equals the concentration of the hydronium ion, or the concentration of our acid, times the concentration of our hydroxide ion. Another good thing to know about this is that Kw equals Ka times Kb. These are all good things to know. These are on your, I believe this one is on your AP Chemistry reference sheet. This one comes in handy later on. So know that Kw equals 1 times 10 to the negative 14th, and know Kw equals the equilibrium constant for acid times the equilibrium constant for the base. Alright? Let's talk about the pH scale. So just some foundational knowledge there on water. But let's talk about the pH scale, right? The pH scale goes from 0 to 14 with 7 in the middle. The pH scale isn't just restricted to 0 to 14, it can be negative and it can be over 14 as well, but this is the general jurisdiction for our pH scale. Anything from the 0 to just below 7 pH is an acid. Okay, these are things like battery acid, lemon juice, your stomach acid. These are all things that have a pH from 0 to 7. Anything that is 14 to just above 7, as you can guess, is basic. Okay, so this is things like milk, bleach. All right, these are things that are basic, and then of course, right at 7 is neutral. All right, so that is the pH scale. There's also this thing called the POH scale, which is just the exact opposite. The POH scale goes from 0 to 14, but from 0 to 7 it's a base, and from 7 to 14 it is an acid. We mostly use the pH scale, but it's just good to know that there is a POH scale out there, but it's just the exact opposite. So there's some background with the pH scale, and now let's get into our calculation stuff, where we're actually going to use some math equations. So our math equations, which is some stuff that we did in regular chemistry as well, is we could find the pH by taking the negative log of the concentration of the acid, or H+. Again, that H+ could also be H3O+. It's just that H3O+ is when we include the water. Okay, so they're the same exact thing. So if you see H3O+, it's the same thing as H+. POH is the negative log of the concentration of the base. All right, so if we have the concentration of the base, we negative log it, it'll give us the POH. And then to relate these two, we could know that 14 equals pH plus POH. So if we have a pH of 1, that means our POH is 13. If we have a POH of 2, that means our pH is 12. So all you have to do is subtract your pH from 14 to get pOH, or subtract your pOH from 14 to get pH. And then we got to do the opposites of these, right? What if we have pH and we want concentration of the acid? We just do 10 to the negative pH equals our concentration of acid, and 10 to the negative pOH equals our concentration of base. Okay, so these are how to get pH, and these are just the reverse. If you get pH or pOH and you want concentration of acid and concentration of base. And here is the thing. We could only do these right off the bat if we're given a strong acid or a strong base. If we're given a strong acid or strong base, we could use these guys all day. If we're given a weak acid or a weak base, we can't use these right off the bat. We have to do an ice table. So let's go ahead, let's move these off to the side, and let's do a couple acid-base calculations where we're given a strong acid or a strong base. All right, everybody, so here I have put my equations off to the side so we could use them for later. And then I have this problem here where I gave you 1 times 10 to the negative 5th molarity of NaOH, and I want you to find the pH, the pOH, and the H+. Now, one thing I want to tell you right off the bat is that a lot of these deal with concentration of OH- and H+. Let me just real quick talk about why we can go straight from strong base to these calculations right here. So what they want is they want the concentration of OH-, but I gave you concentration of NaOH, which is 1 times 10 to the negative 5th. Well, remember that since NaOH is a strong base, it will fully dissociate into Na+ and OH-. Well, if the concentration of one molecule over here was 1 times 10 to the negative 5th, if it completely dissociates, we're going to have the same amount of concentrations in Na and in OH-. So that's why we could plug in the concentration of NaOH directly into the concentration of OH-. It is because the NaOH dissociates so much that it's pretty much the same concentrations when they split apart. Okay, so that's just a foundational thing, that when we have HCl, or concentration of HCl, we pretty much have the concentration of H+2 because it dissociates completely. So let's go ahead and get into this problem now. So again, we have 1 times 10 to the negative 5th molarity of NaOH. This is a base because it ends in OH. So that means when they gave us the concentration of NaOH, they essentially gave us the concentration of OH-, which is 1 times 10 to the negative 5th. So right now I have OH-, but I need pH and pOH. And I'm actually going to flip these around because I don't like how I have this set up. But let's set this up now. So now everything we're looking for is on the left side, right? So right now we have OH-, but we still need H+, pOH, and pH. Well, if we have concentration of base, we could find the concentration of pOH pretty easily. All we have to do is take the negative log of the concentration of that base. So let's go ahead and do that. And that is going to give us our pOH, right? Because we started with a base, it is going to give us pOH. So let's go ahead and take the negative log of 1 times 10 to the negative 5th, and we get 5. Okay, and that is our pOH, right? Because we took the negative log of the concentration of a base, it gave us pOH. If we took the negative log of a concentration of an acid, it would have gave us pH. Now that we have pOH, right, we can go to pH. All right, so let's go ahead and let's go and figure out pH. We know that 14 equals pH plus 5, right? Since we have pOH right here, all you have to do is subtract 5 from both sides. So take 14 minus 5 to get a pH of 9. I don't know why I need a calculator for that. I don't need a calculator. So we have a pH of 9. So we now have this guy right here. So the only thing we are missing is our H+, which luckily, if we do 10 to the negative pH, we can go ahead and find H+. So let's go ahead and do 10 to the negative pH of 9 to get an H+ of 1 times 10 to the negative 9 is our H+ concentration. So now we have POH, pH, and our concentration of H+. I just want to show you one more thing. If you don't want to do 10 to the negative 9, that's the easiest way in my opinion. But there's another way you could figure out using that kW that I talked about earlier. What we can do is, I know that kW equals the concentration of H+ times the concentration of OH minus. Well, I know kW is 1 times 10 to the negative 14th. I know that OH minus was 1 times 10 to the negative 5th. Well, that's another way you could go ahead and solve for H+. You could just do 1 times e to the negative 14th, take divided by 1 times e to the negative 5th, and you would still get 1 times 10 to the negative 9th. So just another way to always remember that kW can help you in some way as well. Don't forget about kW, even though I briefly just mentioned it, kW can be our friend as well. Let's go ahead and do another example that deals with a strong acid. So in this example, I have 1.2 molar HCl and I want to find pH, POH, and OH minus. What you need to do at the beginning of all these problems is look at our acid and say, is that a strong acid? And then you say yes, okay, cool. We could go straight into using these equations over here. If it's not a strong acid, it's a weak acid, we'll have to use an ice table, which we'll talk about here in just a little bit. So right now I have 1.2 molar HCl. So right now the only thing I have is the concentration of the acid. I only have H+. Again, that is because HCl fully dissociates. So right now I only have concentration of H+. Well, let's go ahead and figure out pH, POH, or OH minus. The easiest thing to figure out right off the bat is pH, right? If I take the negative log of 1.2, that will give me the pH, no problem. So I'll take the negative log of 1.2, and my pH is going to be negative 0.0, let's go 79. That is my pH. Again, do not worry. If it is negative, you'll have negative pHs sometimes. Not extremely negative, but slightly negative, okay? Let's go ahead and figure out POH. Now, we have pH. Let's go ahead and figure out POH because it's just 14 minus our pH, which will give us our POH, which is now going to be 14.079. So now we have POH. And now we just got to figure out OH minus, which is just 10 to the negative POH. So we'll go ahead and take 10 to the negative 14.079. And we should get a concentration of 8.34 times 10 to the negative 15th molarity of OH. Alright, so now, pretty simple, we are just plugging and chugging. We should already be pretty familiar with this. Now let's go ahead and step it up a notch and let's see if I don't have a strong acid or a strong base. Alright everyone, so I have a problem here. It says calculate the pH of 1 times 10 to the negative 4th molar solution of acetic acid at Ka 1.8 times 10 to the negative 5th. So it wants pH. So if this is a strong acid, I could just take negative log of H+ and get pH. But here is the problem. This is not a strong acid. This is a weak acid. I see HC2, H3O2, I say that's not a strong acid whatsoever. I could also look at my Ka and see that my Ka is extremely small, and I could say that is not a strong acid as well. So we can't just do the simple thing of just plugging and chugging with the negative log of H+. So what we have to do is we have to use our nice handy dandy ice table. Alright, so first thing we got to do is we got to write down the dissociation reaction of this acid. That's why we did that in our previous lesson. And luckily, we are pretty dang good at realizing that all acids only donate one H+ at a time. So it's just going to break up into H+ and C2H3O2. And then we'll put our ice down the side. And what we are looking for, right? When we want pH, we take negative log of H+. But since acetic acid doesn't dissociate, we don't have any H+ at the beginning. So what we're going to have to do is we're going to have to do an ice table to find H+ at equilibrium. Once we find H+ at equilibrium, we could take the negative log of that H+ and find pH. So really we're just doing the same thing, we're finding H+, but we have to use a long process of using our ice table in order to figure out that equilibrium concentration of H+. It's fine with strong acids because it just completely dissociates and you know what it's going to be, but here it's not completely dissociating. We got to use a little bit of our expertise from equilibrium to help us figure this out. So let's go ahead and do that. Initial concentrations. They gave us an initial concentration of acetic acid. It was 1.00 times 10 to the negative fourth. And we're not going to have an initial concentration of either our H+ or our acetate ion, okay? We're just not going to have those because it doesn't dissociate completely. We're going to look at the change. It's going to be negative X plus X plus X. It's usually always going to be ones all the way across the board because acids are only donating one H+ at a time. So it should always be negative X plus X for these acid ice tables, but be ready for anything. Who knows what the AP will throw at you. And then we combine them for our equilibrium. So we're going to have 1.00 times 10 to the negative fourth. We're going to have X, and we're going to have X. And then, of course, we can't do anything with these equilibrium concentrations unless we have a Ka expression, right? Now, instead of an equilibrium expression, it's a Ka expression or an acid equilibrium expression. So we're going to do Ka of products over reactants, which is H+ and C2H3O2. You can assume all these are aqueous except water, right? If you see water in here, that just means it's going to be H2O liquid, and then this guy's just going to become H3O+ instead. But we just get rid of water altogether because it's a waste of time and we're lazy, so we don't want to include water. So it's going to be the same thing if you do include water. It's just that this is going to be H3O+ instead of H+, but they're the exact same. So this guy's still aqueous, so it's going to be HC2H3O2. After all these years, I still have trouble remembering the formula for acetic acid. I'll remember it one of these days. And then we just plug in what we know. We could plug in Ka because we know Ka they gave us, which is 1.8 times 10 to the negative fifth. We know H+ and C2H3O2 are both X. I'll put them in parentheses. I know we can make them X squared, but I just like keeping things as they were. And then this guy is going to be, sorry, I forgot my minus X here. You guys have probably been screaming at the computer this whole time. You forgot your minus X. Well, good on you. All right, this is going to be 1.00 times 10 to the minus fourth minus X. So now you might be asking, can we assume that X is 0 at the bottom like we have in previous? Is that Ka small enough to assume that the X is just 0? Yeah, okay, the AP is not going to expect you to use the quadratic formula. If you ever get in a situation where you're doing math and it looks really complicated and you think you're going to have to use the quadratic formula, okay, that just means go ahead and assume that the change in x is 0. That Ka is so small that not a whole lot of this dissociated, so we could just assume that this change in x is so minuscule that we could just exclude it. Okay, so go ahead and do that. My rule is usually if it's -5th or lower, so -5th, -6th, -7th, -15th, you could assume that the x is 0. But again, if you get into any complicated maths, you could just go ahead and assume that x is 0 to make it easier on you, because the AP isn't expecting you to do those crazy maths on the exam. So let's go ahead and let's simplify this as much as we can. We're going to multiply 1 times 10 to the -4th on both sides. Okay, that way this cancels out. And then this guy is just going to become x squared. But let's go ahead and let's simplify this out as much as possible. So I'm multiplying 1 times 10 to the -4th times 1.8 times 10 to the -5th, and I get 1.8 times 10 to the -9th equals, and x times x is just x squared. I go ahead and I square root both sides to get x. And my x is going to equal 4.24 times 10 to the -5th. So that is my x, which is important, right? Because remember our overall goal. Our overall goal is to find pH. Well, in order to find pH, we got to have this concentration of H+ so we can negative log it. Well, guess what? We have just found it. We found it by going through our ice table, doing a little maths here and there, and figuring out what x is so that we could figure out that the equilibrium concentration of H+ is that right there. So let's go ahead and let's negative log this guy. So we are going to, let me move it down here. We are going to negative log 4.24 times 10 to the -5th, and that will give us our pH of 4.37. Okay, pH of 4.37. So that is how we are going to find pH, POH, OH minus, H plus from our ice tables if we get a weak acid. We're just going to set up another ice table, go ahead and solve for H plus at equilibrium, and then go back to our original equations of minus log of H plus equals pH minus log of OH minus equals POH, things like that. All right, let's do a couple more examples and then we'll be done. So here we go, everyone. We want to calculate the pH of HOCl with a Ka of 3.5 times 10 to the -5th with a concentration of 0.100. So first thing, I want to calculate or figure out if this is a strong acid or a weak acid. HOCl, that's a weak acid. It's not HCl, it's HOCl. So it's a weak acid, so I'm going to be needing an ice table. And they give us a Ka that is pretty small, so that tells me it's a weak acid as well. So let's go ahead and let's write our dissociation equation, right? It's going to donate 1 proton at a time. And we're going to put our ice table here. All right, let's get going. Initial concentration. They only gave us one initial concentration, and that was of HOCl. Nothing for H plus or OCl minus. Remember, we want pH, so we're going to need that H plus at equilibrium. Change is minus x plus x plus x. Combine them at equilibrium. All right. So now we got to go ahead and set up our mathematical expression in order to solve for x. We know that Ka is going to equal products over reactants, which is H plus OCl minus over the concentration of HOCl. And then let's go ahead and plug in what we know. Our Ka is 3.5 times 10 to the -8th. Our H plus is x. Our OCl minus is x. And our HOCl is 0.100 minus x. Once again, you might be saying, all right, this looks like it get complicated. Can we assume this x is 0? Yes, we can. That Ka is so small, the change is going to be pretty minuscule because it's not going to dissociate a whole lot. The concentration is going to pretty much be similar to what it was at the beginning. So let's go ahead and let's change this to 0. Makes it a lot easier for us. And let's go ahead and simplify. I'm going to multiply by 0.100 on both sides. All right, and then I know x times x equals x squared. So I'm going to end up with 3.5 times 10 to the negative 9th equals x squared. I'm going to square root both sides and get x equals 5.92 times 10 to the negative 5th. Well, what is x again? It is my H plus at equilibrium. So now we just negative log that guy to get pH. So negative log of 5.92 times 10 to the negative 5th is going to give me my pH of 4.2. We'll go 3. All right. So that is that. Let's go ahead and try something a little bit different here, and where we're not necessarily solving for H+, but maybe where we're trying to solve for Ka. All right, here's a little challenging problem for you. At 0.250 molarity, HF dissociates in water to have a final pH of 5.75. What is the Ka of HF? Well, if we're going to be doing anything with Ka, we probably need a Ka expression. So let's look at the dissociation of hydrofluoric acid. Again, it's only going to lose one proton at a time. And this one is pretty simple, H plus and F minus. And it's going to want Ka, so I'm going to need the concentration of H plus at equilibrium, F minus at equilibrium, and HF at equilibrium. And right now, I don't really see a clear way to figure out any of those. So let's go ahead and let's write an ICE table and see if we could plug in what we know. Anytime you see Ka, you're going to be thinking ICE table anyway. So let's go ahead and write our ICE table, and let's write down our initial concentrations. Right now, the only thing I really have is 0.250, and then these guys are going to be 0. And then we'll write down our changes, negative x, plus x, and plus x. Now, before we do equilibrium concentration, let's figure out if they gave us anything that could help us figure out our equilibrium concentration. Well, one other thing they gave us was pH, right? To have a final pH of 5.75. Well, if we have pH, what else can we figure out? We can figure out H plus. If we know pH at the end of the solution, at the final solution, and we just take 10 to the negative pH, it'll give us H plus at equilibrium. Well, heck, that gives us X, and we could figure out the rest of everything. We could plug it into an equilibrium expression, and we got Ka. So let's go ahead and do that. Let's go ahead and take 10 to the negative pH, which was 5.75. So 10 to the negative 5.75 gives me an H plus of 1.78 times 10 to the negative 6th. Right? I'm going to put that over here too, just so I don't confuse anybody. You might be like, haha, too late, Mr. Dahmer. Anyway, so H plus, and we did that just by taking 10 to the negative pH. Well, remember, initial plus concentration equals equilibrium. So that means that 0 plus x equals 1.78 times 10 to the negative 6. That means that x equals 1.78 times 10 to the negative 6. Let's go ahead and fill some things in. 1.78 times 10 to the negative 6, I know that. And I know this is going to be 0.25 minus x equals equilibrium. So 0.25 minus 1.78 times 10 to the negative 6 is going to equal my equilibrium concentration right there. So 0.25 minus 1.78 second e to the negative 6 is going to equal 0.249998822, which makes sense, right? We won't assume a lot of this to change because HF is a weak acid. Let's go ahead and write our equilibrium expression and plug in what we know. H plus on top, right? F minus on top as well. And concentration of HF on bottom. Now let's plug in what we know, all those equilibrium concentrations, right? So we have 1.78 times 10 to the negative 6 times 1.78 times 10 to the negative 6 over our concentration of HF at equilibrium, which was 0.249998822. I don't think there'd be much difference if you left it as 0.250. So 1.78 second e to the negative 6 to the squared to save some time, divided by 0.249998822 will give me a Ka of 1.27 pretty much times 10 to the negative 11th. 1.27 times 10 to the negative 11th. That is my Ka. So be ready for questions like that, where they give you just maybe the concentration of HF, they give you pH. Well, remember, it can always go back to H plus at equilibrium. And then once we have X, we got everything figured out. So that is some equilibrium concentrations. We can also do this with Kb. If you want to be done now, go ahead, because I know this video is running long. But let me do one example with Kb so we know that this just doesn't deal with acids, but it deals with bases too. All right, everybody, so let's do a calculation with an ice table with a weak base. I'm looking at this guy and it says calculate the pH of 0.75 NH3, and it says Kb equals 1.8 times 10 to the negative 5th. This is a weak base, but it wants pH. Pay attention to that, right? It wants pH. So we have a weak base right now, so anything we solve for, remember, that's going to be on that pOH side of the scale. So we got a weak base, we're going to have ice table. Let's go ahead and write our dissociation of NH3. And with weak bases, I like to include water. Okay, remember, water is not included in equilibrium because it's going to be in its liquid phase. If it's in gas phase, you can, but with acid-base reactions, we always assume it's liquid. And it's going to form NH4 plus and OH minus. Sometimes I think it's weird to not include the water just because you're like, where did that OH minus and extra H come from? So I like to include water in my dissociation equations when it comes to a weak base. Let's go ahead and write our ice table. And let's write down what we know. We know my initial concentration is 0.75. I know I'm not including water whatsoever because it's a liquid. And these are 0. Minus X plus X plus X. I got 0.75 minus X. I got X and X. And here, remember, since it's a base, we're not looking for H plus anymore. We can't because there is no H plus, right? We're going to be actually looking for OH minus. If we could find the equilibrium concentration of OH minus, we could find POH, right? Because we could take the negative log OH minus, get POH, and then we could go ahead and transfer that to pH later on. Let's go ahead and let's fly through this thing so I can be done with this video. I know I'm taking up a lot of your time, so I appreciate you sticking around. This is going to be X squared, right? Both of those are on top. This is going to be 0.75 minus X. And Kb in this case is 1.8 times 10 to the negative 5th. Right, again, we're going to assume this X is 0 because Kb is so small. And now let's do a little plugging and chugging to figure out X. So I'm going to go ahead and take 0.75 times 1.8 second e to the negative 5th, which is 1.35 times 10 to the negative 5th equals X squared. I'm going to square root both sides to get an x of 0.0037, which again is my OH minus now. My x is my OH minus. So let's negative log that OH minus of 0.0037. And I get a POH of 2.43. And some of you will be like, done. Remember though, this is a base. We don't want POH, we want pH. So at the end, I'm just going to take 14 minus my pH, or POH, sorry. 14, I'm not smart enough to do this in my head. And I get 11.57 as my pH. Okay, that is it, guys. So we're doing calculations where, first of all, we're looking at our problem saying strong acid, strong base, or weak acid, weak base. If it's a strong acid, strong base, we go straight into negative log H plus, 10 minus pH, things like that. If we got a weak acid or weak base, we're looking at an ice table of some sorts, and we're going to have to find that X, which we could then negative log, and it'll either give us POH or H plus, like in our previous examples. That's it, everybody. Thanks for sticking around. Let me know if you have any questions. Have yourselves a great day.